Testing, 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 testing. Okay, I think we're good. The volume's a little low, but let's tune it up and let's get started. Testing. Testing. Perfect. All right, everybody, happy Monday. Hope you had a great weekend. Today we are going to be looking at a paper, specifically NeRF Art, Text-Driven Neural Radiance Fields Stylization. A recent paper, 15th of December, 2022. This is the work of a variety of different groups here. You have everything from Snap, Netflix, Microsoft, Cloud. It looks like the main group is out of University of Hong Kong, and then I assume the Hong Kong Polytechnic is a kind of like a sister school to University of Hong Kong. But super cool demo. So this is the actual demo page here. The github.io, you see we have a NeRF, and then they're able to apply a style transfer to that NeRF. So someone has finally combined the text-driven AI art or image generation and mash it together with NeRFs to create cubism painting. These are, yeah, the quality is good for this. So we're going to be looking at this and excited to read. So let's see how they do it. This is their GitHub. And this is the paper, which I have open in PaperPile, which is basically a paper management tool. Not sponsored by them, but I would love to be sponsored by them. Wow. So getting started, a powerful representation of 3D scenes, the Neural Radiance Field. So this is what NeRF stands for. And it's a machine learning model that contains the representation of a scene in its weights. Stylizing NeRF remains challenging. Okay. Paper, we NeRF Art, text-guided NeRF stylization approach that manipulates the style of a pre-trained NeRF model with a simple text prompt. Our method can change. This is achieved by introducing a novel global local contrastive learning strategy. Okay, they'll probably describe that, but again, contrastive learning is when your objective is to compare points in a embedding in a latent space and push those apart or pull them together depending on some kind of high level thing. Combined with a directional constraint, okay, to simultaneously control both the trajectory and the strength of the target style. Okay. Moreover, we adopt a weight regularization method to effectively suppress. Okay, so they have some extra bag of tricks here. To suppress cloudy artifacts and geometry noises which arise easily when the density field is transformed. demonstrate that our method is effective and robust with both single view stylization quality and cross view consistency. Code and results can be found there. Cool. We'll check out the code eventually, but I wonder if it actually works. Clone, recommend. Okay, this actually looks like it's there, right? Our implementation is based NeRF multi-view 3D reconstruction using neural rendering, unofficial implementation. Okay, this is some other random person's NeRF. So most NeRFs you see on the internet are made NVIDIA GitHub, called like NeRF Lab or something. So maybe they use this other implementation here for licensing reasons. This is a MIT license, so it goes on there. Artistic work, world in various creative blah blah blah. Generation of artistic content is now more accessible to average users. By impressive results, these methods are limited to stylizing a single image captured by the content. Stylized 3D content from a implicit representation of a neural radiance field. So implicit there would contrast the explicit representation mesh and a texture, which is what 3D objects usually are represented as, right? A collection of every single point in little triangles, and then the color that each of those faces of that mesh, way that they reflect light, all of that is explicitly stored usually for 3D stuff. But in NeRFs, it's all implicitly stored, right? It's all just stored inside some neural net, and the neural net has some idea of what the object looks like from different views. So there are some other people that have already started doing some stuff here with NeRF stylization. Stylization with natural language is no longer a fantasy. Yeah, I think the natural language is IMO the ultimate user interface here, and I think it's going to continue to be the theme for flexible control and user-friendly way to specify styles. Okay, train NeRF model in a single text prompt. Our method enables novel view spaces with both appearance and geometry. This is achieved by combining the recent large-scale language model. All right, so they're using clip here. Everyone's favorite MIT licensed language vision model. They design a clipped-based contrastive loss. And here's your contrastive loss, right, where you're bringing some stuff closer and other things farther away. So they're using negative samples. So the loss is on the distance in this embedding space. Relax the constraints on the density. Okay. So a lot of these NeRFs, they have kind of ways to make the density more dense in some places and less dense in others, right? We've seen in a lot of these papers where they try to make NeRFs more memory efficient. One way to do that is just reduce the amount of points, and anything that's a low density region, you just don't have any information there, right? So right, for a NeRF, you have some volume of space, and then you're projecting these rays, and then along that ray, you can sample points, and then the model will tell you the density at that point, which is basically whether or not there's something actually there. And reducing the number of points that you have to sample and having larger spaces of your volume be empty is a good way to kind of reduce the inference and the general compute footprint. So it seems like they had to kind of maybe relax some of those in order to get the style transfer to work a little bit better. Conduct a user study to show that our method of... Yeah, I like this too. So we've seen this in some of the previous papers we've looked at, where in some of these generation papers, right, you have to basically, at the end of the day, you have to come up with some metric to say, hey, is our images or our NeRFs better than the previous or some other works images and NeRFs? And the hard part is that it's very subjective. So some papers choose to use these kind of like quantitative metrics such as Richet inception distance. But I think the gold standard is kind of emerging, which is to have these kind of user studies where you have people sit there and stare at pictures, A or B, and they like pick which one they want. And then that allows you to collect a bunch of data and say, okay, it seems like people like picture A more than picture B, and so on. And I know that the kind of user studies are more expensive, and maybe they act as a barrier for people with less resources to do machine learning research in this field, in kind of the image generation and generating subjective content. But I do like these user studies much more than the kind of like bogus metrics like Richet inception distance. Damn, look at this. They're referencing 1998 and 2001 papers. That's hardcore. Yeah, mesh stylization. So this is just kind of a nice little summary of all the different stuff. You have 2018 work. Now you can see some people here still using GANs or ConvNets. This is a very extensive related work section. This is, whoever did this part of the paper, hats off. This is a lot of work. Someone actually went and really dug deep into the literature. Yeah, so it seems like a lot of the previous work use reference images, but in this work they're using text prompts. There's not a huge difference in that, because I feel like the people who use reference images are probably just using something like clip to bring it into an embedding space anyways. But I think text prompts are kind of, I do agree with the argument that text prompts are a little bit simpler and a better user kind of interface than using an image. Here we go, boom. He literally said this next sentence is exactly what I just said. Compared to image references, a natural language prompt is a more intuitive and user-friendly way to specify the style. They put a couple different works here, StyleGAN and text to mesh, which both use clip embeddings to do style transfer. We'll go back and we'll look at the papers. Avatar clip further supports using natural language. Oh, that's interesting. Paper where they're using stylized human mesh using natural language. Yeah, I think the problem is my maybe contrarian opinion is that triangular like meshes and textures are eventually going to disappear and all 3D content will be based around NeRFs. I know that still seems like it's impossibly far away and there's so many programs, so many game engines, like the entire CGI pipeline is based around meshes and textures, but I feel like NeRFs are just so much more efficient and ultimately a better way to represent 3D information that I see all of that going away, all mesh and textures going away, and eventually the world just moving into NeRF-based and neural-based representations for scenes and people and even styles. We focused on introducing, okay. They have their directional clip loss. Then they have their global local contrastive learning framework, which I think is what they're doing here. Next, they introduce the weight regularization term, little bag of tricks. And overall strategy, okay. Nice little overview of the papers. Like this is a well-written paper. You know, I like these figures. I like the nice, thorough related work section. This is good stuff. Whoever wrote this, Kan Wang and Ri Xiangjiang, like, well-written paper, guys. All right. So let's get into it. So NeRF is the 3D representation. So I forget what the colors we were using were. I think we were using maybe this red color for green color for definition. So we have a spatial coordinate x, y, z. That's just a point in 3D space. And then there's a view direction d. So that's theta and then phi, right? Like it's the pitch. Where are you looking at? The network predicts the density sigma and the view dependent radiance c. So density sigma is going to basically, some people call this transparency, but it's basically that point in 3D space. How see-through is it? And it's like a proxy for how hard the material is. And then this view dependent radiance is basically a color. It's just like, what is the color of that point in space? But they call it radiance because it's not necessarily the color of the cup, right? If I'm looking at this cup, there's a specific angle. Right now it looks like this like white color, but there's a point at which I'm going to cross the beam of the light that's reflecting off of it. And when I go through that point, the individual little point on this cup is going to suddenly turn very bright, like a different color, and then it'll go back to the color it was before. So depending on the view, right, the color of each point on some scene or in an object is going to change because the lights are bouncing off rays, right? Okay, and then they have the final color, CR, of the camera ray, which R of t, which is O plus t times d, right, where you have d as the view direction, and that's done by accumulating k sample points. So I think this is a picture to think about here. So this ray here, you have this volume in space, right? You have points in this volume parameterized by x, y, and z. This ray, right? A ray is just another way to say kind of like a vector. It's like an arrow, right? This red arrow. You're sampling along it, right? So each red dot here is a sample along that arrow. You have t samples. Each of these samples has some color, right? C, and it also has some density, sigma. And remember, this ray, you can also say the view direction of this ray is parameterized by theta and then phi, which are basically define the view direction of that. So I think that's the x and the v here. X is the spatial coordinate, and then what is v? I guess v is the... Where are you defining v? Maybe they meant to say d. It doesn't seem this stylized letter V here. But anyways, then this is your actual NeRF, right? Your neural radiance field is actually this little function right here, is this neural net, which is these 3 bars of purple here. And this neural net takes basically the ray and the view direction, and then it'll tell you the density and the color at each point you sample along this ray. And then right here you have a plot of the density, and then the d, the distance along that ray, right? And you kind of add all those up, right? And then you get the final color. So if you have multiple samples, right, and you have the first one is see-through, then the final color is going to be the sum of all the see-through stuff. And what a lot of NeRF papers actually do is they're a little bit more clever about this, where, right, if you have this point here on the face, all the points behind it aren't going to make a difference, right? It's like once you have kind of a peak in this density function, then you can almost just stop sampling along that ray because you're going to know what the color is. So there's little tricks like that you can use, but I think in this paper they weren't necessarily concerned about the total inference time. But yeah, that's how you go from a view angle and a neural radiance field into a image, and then you simply have a reconstruction loss that tries to make the resulting image look like the image that you're trying to get the NeRF for, and that's how you train this NeRF. So that's how you train this part here, the reconstruction, or the NeRF, which is using a reconstruction loss. Okay. So they have here the final color at a camera ray, which is basically the pixel. Each pixel is going to have a camera ray, and there's going to be, you want to know what the final color is at that pixel. You're summing up all the Ks, all the samples along that ray. You have 1 minus this omega K here, which is the transmittance of the ray segment. right? Which is basically just the view direction times the density from k to k+1. And then tk is the accumulated transmittance from the origin to the sample k. Right, so this is what we're saying. It's like you kind of add up these points as you get closer and closer to, or as you go further and further from the ray. As your ray travels through the volume, maybe is a better way of saying it. Train a NeRF from a set of multi-view photos, a semi-simple supervised reconstruction loss. Then you have the ground truth pixel colors, which is your CR. This is your the actual image that you're trying to make a NeRF for, right? C hat R, and then that's your target color, and then the color that your NeRF outputs is CR. So your reconstruction loss is just basically the difference between the color and what you want the color to be for all rays. So this is all pixels in the image or rays, because each pixel corresponds to one ray. So this is also why NeRFs can be very compute intensive to create, because this image here, right, let's say it's 256 pixels by 256 pixels. For each of those 256 by 256 pixels, you have to get one ray, and then each ray itself has k sample points. So it's a lot of computation, right? Because each sample point along the ray requires one inference. You can definitely batch it, but still performing inference for each point. And then each ray, like there's one ray for each pixel. So the total number of inferences required to generate one picture from one 2D image from a NeRF is high. Okay. After optimizing the reconstructed NeRF model, FREC. So this is the NeRF. This is a neural network. Our goal is then to train a stylized NeRF model, fSty, okay, which satisfies the style control. The target text prompt here, you have a different, this is the actual TGT text prompt target while preserving the content from FREC. Okay, the clip model aligns the semantics of the image and the text in a joint embedding space using the image encoder. So this is just pre-trained clip, which you give it an image, and it'll give you a point in a embedding space. And then you have this text encoder, which is also basically pre-trained clip. And you give it a text, and it'll give you a point in that same embedding space. And then you can basically say, I want the point in the embedding space that when I feed the image through the image encoder to be as close as possible to the point in embedding space when I feed the text into the text encoder. Yeah, so here now they're talking about a couple problems that you run into when you try to do this. You have this kind of washed away, proper strength, and maintains cross-view consistency and avoids artifacts. So these are just some of the problems that they run into when they're just trying to do this. And this is probably where the bag of tricks that they'll introduce later come into. So you have a stylized NeRF rendering target image and the target text prompt, which we had before. This is the loss. So a directional loss here, you have it's summing over the target image. You have 1 minus, this is the encoder of the target image. This is the encoder of the target text. This is a cosine loss, I think, these little like arrow brackets here. And then you have 1 minus that, right? Cosine similarity. Yeah, they're defining it here. I was going to say, I don't really know if that's, there's like a deep generic mathematical script notation for cosine similarity loss, but they're defining it here as parentheses, triangle, arrow bracket. Cosine similarity is, right, these encoders, they give you a point in embedding space. A point in embedding space can also be called a latent vector, right? And if you think of a latent vector, you can, best way to describe, yeah. So here you have the latent vector that represents hello, comma, world, and the latent vector that represents hi, comma, world. And if you take the cosine between those, basically the closer those are in this embedding space, the more the kind of dot product is going to correspond, right? So 1 minus that here basically gives you a measure of how close these 2 points are in space. This global loss could easily mode collapse the generator. Source image here. A pair of text prompts instead of a single one. Okay, so basically what they're saying here is that when you're just when you take the latent vector of the target image and the latent vector of the target text and just get the cosine similarity between those, you end up in this mode collapse of the generator. It means the model just doesn't train well. So what they did instead is they here they do the difference between the target text and the source text, right? The difference between those two latent vectors, the difference between the two image latent vectors or embedding points in the embedding space. And one thing that this reminds me of is word embedding space difference and that. Yeah. This is like kind of an older picture now, but for example, in like the latent space of a large language model, right? So you could think of this as the points in an embedding space or a latent vector. The distance between king and man, like that vector, is actually very similar to the vector between queen and woman, and that vector itself is royal. So basically the distances in embedding space, right, these latent vectors actually have meaning. So I think that's a useful image to have in mind when you're looking at this and saying, why are they doing the difference between the two image vectors and the difference between the two text vectors and then doing the cosine similarity between those. So basically, they're looking for the cosine similarity between these two red vectors rather than the two blue vectors. Propose a contrastive learning strategy to control the stylization strength. Figure 3C. Yeah. With the rendered view as the query target, we set positive samples to the target text prompt. Construct negative samples, which are sampled from TNeg, the set of negative samples, by sampling a set of text prompts semantically irrelevant to target image. Okay, so for each image, right, maybe you have human and zombie, and then they have, here are the negative ones, right? So they want the latent vectors or the points in this embedding space to get closer to zombie and further away from Princess Elsa, sketch, and so on. So you need the pull together. For these contrastive losses, you want like the pull, where you're pulling your image closer to zombie, but then you also want the push, where you're pushing it away from Princess Elsa and sketch here. And the choice of Princess Elsa and sketch is kind of their, I don't know how they're picking these, right? These negative samples, right? How do you determine what a semantically irrelevant negative text prompt is? For the case of this paper, they probably just came up with those themselves, but I wonder if you could have a more general way of doing that. All right. So this is the contrastive loss here. And you can see how it's, you have here the query, the positive sample, and the negative sample. So this looks a little confusing because there's log here, but it doesn't actually matter because you have logs of exponents here. Right, so the log cancels out the exponents, and the reason they do this is because log properties sum. The nice thing with logs is that the logs of two things multiplied is the same as the logs of two things added together, and the logs of two things subtracted is the same as the log of two things divided, right? So whenever you see exponents and logs, most of the time, the reason people are putting those in there is because they want to basically reduce these equations and make them simpler, right? So here, basically, this is actually subtracted from this, and then these two things are multiplied together. Let me actually do that. So that's all they're doing there, right? And really all you need to think about is that what this contrastive loss is doing is it's pulling things together in this embedding space, and then it's pushing things apart in this embedding space. And you're summing that over all of the target images. They also have this temperature T or tau. And then they have a global contrastive loss. Okay. So they have this global contrastive loss, but then they found that if you kind of have only a global contrastive loss, you're going to get excessive stylization on certain parts and insufficient stylization in other regions. So what they're going to do is they're basically going to break up the image into random local patches, where instead of the whole image, now you're just looking at a small patch of that image. That's P target, which is just cropped from I target. And then you're going to apply the local contrastive loss on those little targets and combine it with the global contrastive loss. So you're doing the style transfer on little individual image patches, but then also on the whole image itself, and you can trade off with these gammas here. That's not gamma, what is that? Lambda. Let's go back up here now that we've gone through this. So the absolute directional loss, B, the relative directional loss, and C, the global and local contrastive loss. So this is the cosine similarity between just the target image and the target text, right? So this script letter E here is the embedder. It's just basically clip, right? The pre-trained big model that they got from the OpenAI repo. They're feeding their target image and they're feeding the target text prompt. And then you get a vector, and then they're basically saying the cosine similarity between those. This part B here is the queen king thing that I was explaining here, where now you're not just doing the difference between the two vectors, you're actually getting the difference between the text. So here you have they're just coming up with what the text prompt of their source image is, right? Which is another kind of little hand wavy thing they're doing here, where they're deciding that this image that they picked is human. But they're saying, okay, the difference between the embedding point when you encode it with clip for human and the same thing when you encode zombie, that vector, compare it to the vector of the source image to the target image, right? And this gray sphere represents the embedding space, right? The latent manifold of a clip pre-trained model. And then here you have the contrastive loss, right? And you have the global one, which is the whole image. And then you have the little local one, which is the little patches, which is little crops of the image. So this is the different contrastive losses that they're using. Okay, section 4.3, artifact suppression with rate regularization. Our pipeline aims to change not only the color, but also the density. Yeah, so this is interesting. They were saying appearance and geometry, right? And color and density, and then they're basically saying that color is appearance and density is geometry. So there's kind of a weirdness there, right? Where the reason that people refer to like the mesh part of a texture. So in the classic way of defining 3D objects, you have kind of a texture and a mesh, which is a bunch of vertices with triangles. And people will refer to the mesh as geometry, right? Because it's made of triangles. But in a NeRF, you don't have this triangular mesh anymore. It's all just inside a neural net. And to the neural net, the color and the density are basically the same thing. They're just a number that it's predicting when you give it a view direction. So it's interesting here how some of the terminology from the original kind of way that we do 3D with textures and meshes is kind of seeping into the NeRF terminology, where now people are referring to the color part that the NeRF outputs as the appearance, and then which would normally be the texture, and then the density that it outputs as the geometry. So maybe a little bit of the kind of historical context as to why this kind of terminology is the way it is. Okay, so then they have a weight regularization loss to suppress geometric noise and encourage a more concentrated density distribution. The weight of each ray sample is defined as the contribution to the final ray color. Similar to the distortion loss, the weight regularization loss is, here you have the loss. And this is a good, so remember how earlier we were saying that the NeRF, there's so many parts to it, right? For each pixel in the image, so over all target images, right? So you have a variety of different target images. Each pixel in that image has a bunch of ray, or has a ray, so basically the summation over R is every single pixel in each target image has a ray, and then each ray itself has a bunch of randomly sampled pairs, I and J, K of them. And here what they're basically saying is they want the distance between these to be small. To suppress noise peaks and aggregate weights to the correct objects. So basically what they're saying here is, you see how in this ray that goes through our volume here, you have these 4 points here, right? Most of this ray should be crossing empty space, right? In kind of picture, in like this kind of NeRF of a human head, really you should have a bunch of empty space, and then you're going to hit the face, and there's going to be a lot of density very high, and then the rest of it should be empty space again, right? So like the function of density over the distance of the ray should basically be nothing, 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 then one big spike, and then nothing, 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 right? And that represents the surface of the object. So what their loss is doing here is it's basically saying each of those little red points along that ray, we want to add this regularization that kind of makes those closer together. So you don't have a situation where you have kind of like random floating points far away from the face, which is what they like. And the interesting thing is that you kind of want to play with that, right? Because there's going to be some styles, specifically for example this one, where you take this like T-Rex and then you change it to colorful galaxy. Like some of the styles you almost want them to become a little bit more diffuse, and then in other styles you want them to be more crispy, right? So like there's this kind of trade-off between kind of the fuzziness and the transparency and the kind of how I don't know what the right word is here, but like diffuse the 3D stuff is versus how crispy the edges are. And I think this regularization kind of allows you to maybe play with that. Okay, so training, they have all their losses here. They have the text-guided stylization loss, which includes the directional clip losses and all of their contrastive losses. They have the content preservation loss. Okay, which is a VGG-based perceptual loss. VGG is a convnet, right? And it's basically you're taking two images, feeding them through a convnet, and then taking the distance of the resulting two embedding points and then saying these 2 points need to actually be close together. I don't actually like this content preservation loss. I feel like there's a better... Someone needs to like innovate on this. And then you have your artifact suppression regularization loss, which is this one up here. It's like point distance loss thing. Yeah, so this is the perceptual loss is based on a predefined VGG layers. So they take the target image, the source image, feed those through a pre-trained VGG model, and say the squared distance, the difference squared between these should be as small as possible. Yeah. Prohibitively huge memory consumption. Okay, so they say there's a couple different ways that people deal with the fact that there's just so many samples per ray, and then there's so many rays per image, and then you have so many images, right? You have multiple target images, multiple source images. So the way that they kind of break up this pipeline so that you can kind of reasonably fit it on a GPU and actually get gradients is they first render all the rays to get the whole image. Then they calculate the stylization loss gradients, right? Because they get the feed forward for the images here. And then now that you've done that feed forward, you can, right, get the gradient of that operation. Then they do it at the patch level. So then rather than backpropping through the whole image, they backprop through each little patch of the image. So they're basically doing multiple patches, or they're splitting up the image into different patches. I think the word for that, but it's for deep learning. There's like a specific image that but basically there's data parallelism, model parallelism, and batch parallelism. In this case, this is, I think, a form of model parallelism, right? Because you're breaking up the model itself into different chunks and then performing the compute for each chunk of that model and then aggregating the result at the end. I think data parallelism is when you split your data across a variety of GPUs. Model parallelism is when you split your model on the GPU. And then batch parallelism is when you split your batch. But wouldn't that mean it's the same as data parallelism? I don't know. I think I'm getting a little, probably messing up my terminology there, but TLDR is that they're splitting the image into patches in order to get the be able to perform the inference and the backprop. Okay, so they're using PyTorch here. They sample 192 points for each ray. So, just for context, right? Each ray is 192 of these red dots. For each dot, you need to run inference once. And there's however many rays per image based on the pixels, so that's a lot. I think they'll actually probably tell us the number of pixels. They train for 6 epochs. The learning rate is 0.005. Probably have some learning rate schedule. Atom optimizer. These are different hyperparameters here. I have 200 text descriptions for interest. 1/10 of the original input, so the patches are basically a 10 by 10 grid. Okay, so the things they're using for the test dataset are 6 video clips in 10 seconds. And then they have 100 frames for each video clip. This is the actual size here. So we can actually calculate it now. We have 270 by 480 images or pixels. And then each pixel corresponds to one ray, which has 192. Yeah, so look at this. You have 25 million inference steps. Like, obviously you're doing it in batches, but that's just how many times you have to perform inference on this NeRF network. Estimate camera poses for these frames using Colmap. With rigid relative camera constraints. They use 256 for stylization. Okay. And they're also using local light field dataset. Oh. So here you have some figures here. Here they're playing with the different phrasings of the text, right? So like this text prompt here is getting put into clip, and then you're getting a vector out of it, and that latent vector or that point in the embedding space corresponding to that text is slightly different, right? Lord Voldemort, head of Lord Voldemort, head of Lord Voldemort in fantasy style, head of Lord Voldemort in fantasy style Harry Potter film. Those are going to have different, those are going to be different points in space. So this is interesting because it allows you to kind of see how the text prompt changes it. Like one thing here, right, is for the Pixar style. Right, you get softer kind of colors here. But when you add 3D render in the style of Pixar, you get almost like more lighting, more kind of reflection. So it's like, what is the word 3D render adding, right? Okay, so this is theirs to StyleGAN. I mean, these kind of look the same, to be honest. comparison section. We compare with the most related works in 3 categories. We have the StyleGAN, text to mesh, and avatar clip. Text-driven NeRF style, so they have clip NeRF field. They use author-released codes. Okay, so I mean, this is actually good stuff here. They're actually saying that they used the original author code, and then they actually went and actually trained and listened to the advice of the authors for each of these papers into how to best use it to make the best possible work. A lot of times when people are comparing and benchmarking to previous work, they're just kind of doing it lazily and just using kind of like the worst version of it. But here it seems like they put some time to actually show the best version of these other previous works. Okay, this is all just kind of like subjective thoughts here, right? It's like we're saying StyleGAN here has inconsistent shapes or textures when you get different views. StyleGAN is less friendly to faces. This is interesting here. So they have their clip guided losses. So you have the original image, and then you have this is the without the local and global contrastive loss. So I mean, you can see that that actually adds a huge part of it. Here, this is the more interesting comparison here. This one and this one. Right, so in here, you have the difference between the global and the local. So this is without the local and without the global. So without the local, they were saying that the global one just kind of only focuses on specific parts. You can see here the ears, and this one almost looks like it made it a cat face. And without the global loss, you don't have the whole image, and you can see how each individual patch is good, but then the whole image kind of loses meaning. You start having like eyes on top of eyes. And then with both of them, it looks quite good. Comparisons to text-driven mesh-based stylization. Limited by the expressivity of the mesh representation, text-to-mesh fails most runs and presents unstable stylization results. Yeah, I just don't think meshes are even worth dealing with. Like, why try to fit the square peg in a round hole? Like, we have NeRFs already. Just do everything in NeRF. You don't need to have these like meshes. So they somehow got the actual mesh. So this is the actual triangular mesh for this image. Because for some of these, right, these text-driven mesh stylization approaches, you need the mesh. Have comparisons. That's a very high quality mesh for this kind of image. This is definitely someone sitting in like a photo volume. How the mesh changes here. Pixar one looks pretty bad. This is the regularization loss that they were doing, where they were making the density of the points closer together, right? So like along that ray, they want the points to be close so that you don't have like kind of random points floating in space. And you can see how without that regularization loss, you get that effect where you have a bunch of points kind of around the surface, and with the regularization loss, you get kind of the crispier, harder surface. Avatar clip requires a 3D mesh. Okay, now you finally get to the user study where they paid a bunch of people to compare. So 50 total comparisons, 5 prompts, and then 10 images for each prompt. Like how lady is capitalized here. I think this, you're going to say outperform. Base it on user preference. Now you have a little section here. Answer some questions. Nice, I like. The directional clip loss can enforce the right stylization trajectory, but struggles to reach a sufficient magnitude, shown in the second column of figure 9. Local contrastive. Because the loss only measures the directional similarity between the normalized embedded vectors but ignores their actual contrast or global contrastive loss can ensure the proper stylization magnitude by pushing as close as possible to the target. Clip focuses more attention on features than on others. Yeah, I think this is a good idea. And this is like people have been doing this in different computer vision stuff for years, right? That you want to, in any kind of pipeline or system, like there's a difference. There's this kind of like there's different resolutions that you need to be performing things at. I think having a contrastive loss at the global level and then at individual patch levels is always going to be a thing. Linguistic ambiguity or semantically meaningless words may result in unexpected. Yeah, I mean, ultimately you're using the embedding space of the clip pre-trained model, right? So what does mouth Batman correspond to in that embedding space? Probably nothing, right? Abstract meshes, marching cubes. Despite the success in most cases, our method still has some limitations. Cool. This is a well-written paper. This is the user study, so you can see that people very, very consistently prefer theirs, the gray bar, compared to the other ones that they compared against. Are there any other images that we missed? Volume, sign distance function. These are simple SMPL human meshes here. They're quite good. You can see how text to mesh and avatar clip, like the global is like maybe the kind of patch versus global isn't quite there, right? Where like you kind of it just looks like the average of what it needs to be versus the kind of crispier details here, like the folds on the elbow and the red lips and the green hair, like all of that is much crispier on there on the NeRF Art. Calling theirs ours. Cool. Code. Sites. Contributors. Okay, so you actually had some contributions as soon as July, and then you had kind of November, December when they pushed it. So maybe that's when they started working on it, and then November, December is when they actually did it. These are the two people that are really working on this are Cassie Python and Songrise. Probably Cassie. NeRF Art, Clip NeRF. Shader, Hyper NeRF, NeRF Art. Student in badass. And we can actually look at the requirements. They have PyTorch probably. Your standard stuff. Cool. So that was NeRF Art, text-driven neural radiance field stylization. Thanks for watching. Extracting meshes is part. Probably. I can't. Yes, probably. But you don't extract this you fire. The images with yeah, they extract the mesh with this here. There's two ways. Use ball SDF here. Ball. Yariv et al. This one, volume rendering of neural implicit search. This is what they're using. Volume implicit search. Ball SD. Allowing to learn high fidelity geometry from a sparse set of input images. This is MIT licensed as well, so that actually looks, these meshes are very clean. Cool. Thanks for listening and see